Hi everyone, welcome to today's lecture on Submicron MOSFET. It is one of the important topic in our low power VLSI design concept. In previous lecture, we have studied long channel MOSFET and understood its structure, operation and characteristics. Now we will see what happens when the channel length is reduced below 1 micrometer. That is called as submicron MOSFET. By the end of this lecture, we will be able to define a submicron MOSFET, explain its structure and operation, understand the major short channel effects, discuss its advantage and design challenges, compare it with long channel MOSFET. Let's start with our recap of previous session. We have seen sources of power dissipation, MIS structure, long channel MOSFET. Today we will move on to submicron MOSFET, which is advantage of long channel MOSFET, that is area constraint, and it is the foundation of modern CMOS technology. Understanding this topic is very important because almost all modern integrated circuit uses transistors with channel lengths much smaller than 1 micrometer. Let us first understand what a submicron MOSFET is. Submicron MOSFET is a MOSFET whose channel length is less than 1 micrometer. In today's semiconductor industry, channel lengths have reduced from hundreds of nanometers to just a few nanometers. Reducing the channel length provides several advantages in terms of area, since the distance traveled by the charge carriers is getting reduced and the transistor switches much faster when this is scaled down. More transistors can also be fabricated in that particular location inside a single chip, which increases the integration density and improves overall performance. Some important features of submicron MOSFET include channel length below 1 micrometer, very high switching speed, smaller chip area, high transistor density, low operating voltage and increased leakage current. These devices are widely used in microphones, smartphones, microprocessor applications, high-speed processor, memory chip and system on chip or SoC devices. Although submicron MOSFET improves speed and performance, they also introduces several new challenges known as short channel effects, which are to be addressed, that will be done shortly. Now let us discuss the structure and operation of submicron MOSFET. Structurally, it looks very similar to conventional MOSFET, as it consists of gate, thin gate oxide, source, drain and semiconductor substrate. The major difference is the much shorter channel length. Length is getting reduced. The operation begins when a gate to source voltage greater than threshold voltage is applied. This creates an inversion channel between the source and drain. Now electron starts flowing from source to drain in an NMOS transistor, while holes flow in a PMOS transistor. However, because the channel is extremely short, the electric field from the drain extends into channel region. As a result, the drain voltage begins to influence the channel more strongly than in long channel MOSFET. This produces several important characteristics like high electric field, fast carrier transport, lower propagation delay and reduced channel resistance. One important point to remember is that when channel becomes very short, the assumptions used for long channel MOSFETs are no longer valid. That is to be considered while designing this short channel. Next, one of the biggest challenge in submicron MOSFET is the occurrence of short channel effect, also called SECs. These effects occur because the source and drain depletion regions become comparable to the channel length. Let us discuss some important short channel effects. The first is threshold voltage roll-off. As the channel length decreases, the threshold voltage reduces, making the transistor easier to turn on before the threshold voltage. Next is drain-induced barrier lowering, which means the drain voltage reduces the energy barrier at source, allowing current to flow even when the transistor is supposed to be off. Third is velocity saturation. Due to high electric field, electrons reach their maximum velocity quickly, limiting further improvement in current. Next is channel length modulation, where the effective channel length changes with drain voltage. And another important effect is punch through effect, where the depletion regions of source and drain merges, causing uncontrolled current flow. We also have another thing, hot carrier effect, where highly energetic electrons damage the gate oxide over time, reducing the overall device reliability. Finally, all these effects leads to increased leakage current, which increases static power consumption even when transistor is not switching. Therefore, while submicron MOSFETs improve speed, they also increase leakage power and reduces the reliability. Advantages and challenges. Now let us look at the advantages and challenges. The major advantages are high switching speed because of short channel and smaller chip size, which is the advantage. High transistor density, low dynamic power consumption, but better overall circuit performance, and supports for advanced CMOS technology. However, these benefits come with several challenges. Leakage power increases significantly. Heat generation becomes higher because millions of transistors operate simultaneously. Manufacturing variations become more critical as device dimension is getting shrinked. The circuit design becomes much more complex due to various short channel effects. To overcome these challenges, engineers use several advanced techniques. These includes high K gate dielectric material to reduce the leakage current, and metal gate technology for better electrical performance, multi-threshold CMOS or MT CMOS to reduce standby power, FinFET technology which improves controlled gate control over the channel, and SOI, that is silicon on insulator technology, which reduces the parasitic effect and improves the speed. Parasitic effect is one of the drawback in long channel MOSFET, the parasitic capacitance that is getting minimized here with area constraints also. And these techniques enable modern processors to achieve high performance with low power consumption. And long channel versus submicron MOSFET, let us compare these two. Here channel length is greater than 1 micrometer, whereas in submicron it is less than 1 micrometer. Submicron MOSFET switch much faster and allow much higher packing density. However, leakage current is significantly higher due to short channel effects. Dynamic power is lower because these devices operate at lower supply voltage, but static leakage power becomes much higher. Long channel MOSFETs are mainly used in analog circuits and educational applications, whereas submicron MOSFETs are used in modern processors, memory chips, smartphones and system on chip devices. Thus, modern VLSI design focuses on controlling leakage power while maintaining high speed and high integration. Let us summarize today's lecture. A submicron MOSFET has channel length of less than 1 micrometer and is a basic building block of modern integrated circuit. Its reduced channel length provides higher speed, smaller chip area and greater transistor density. However, scaling introduces short channel effects such as threshold voltage roll-off, DIBL and velocity saturation, punch through and increased leakage current. To address the above issues, modern technologies such as high K dielectric material, gates, FinFETs, MT CMOS and SOI are widely used. Understanding submicron MOSFET is essential for designing high performance, low power VLSI systems used in today's processors, smartphones and advanced electronic devices. In next lecture, we will study gate-induced drain leakage and explore its impact on power dissipation in CMOS circuits. Thank you all.